Picture a moment frozen in time. The control room at NASA falls utterly silent. Screens flicker with data that defies explanation. The scientists, seasoned experts who have spent their lives decoding the cosmos, can only stare in disbelief. What they've just witnessed shouldn't be possible. A signal from deep space, repeating in a pattern that hints at intelligence, or perhaps a planet where life thrives in conditions that would vaporize steel. These aren't scenes from a sci-fi movie. These are real moments when the universe looked back at us and whispered secrets that left even the brightest minds speechless. For centuries, we've gazed at the stars, convinced we understood the rules of the cosmos. But space has a habit of throwing curveballs, discoveries so unexpected, they rewrite textbooks overnight. Imagine dedicating your life to unraveling the mysteries of black holes, only to find one behaving in ways physics can't explain, or training telescopes on a distant galaxy, only to watch it vanish without a trace. These aren't just anomalies, they're cosmic wake-up calls, reminding us that the universe is far stranger, far more wondrous than we ever dared to dream. That's what this journey is about. The 25 times space scientists were completely, utterly shocked. From rogue planets drifting between stars to signals that might, just might, be messages from another civilization, we're diving into the moments that redefined what we thought we knew. Each of these discoveries cracked open the door to a deeper mystery, proving that the more we learn, the less we truly understand. So buckle up. Whether you're a casual stargazer or someone who devours every SpaceX launch, what comes next will leave you questioning everything you thought you knew about the final frontier. The universe is waiting, and it has surprises in store. The night of August 15, 1977, started like any other at Ohio State University's Big Ear radio telescope. The machine scanned the sky as it had for years, listening for the faint whispers of the cosmos. Then, at 10:16 p.m., the universe shouted, a signal so powerful, so precise, it made astronomer Jerry Amon circle it on the printout in red pen, scrawling one word beside it: wow. That single word would give the signal its name, but the mystery behind it would haunt scientists for decades. For exactly 72 seconds, a narrowband radio burst blazed from the constellation Sagittarius. It wasn't random noise or interference. The signal matched the exact frequency scientists predicted an extraterrestrial transmission might use. The hydrogen line at 1420 MHz, a quiet channel where cosmic static fades away. And then, just as suddenly as it appeared, it vanished. Big Ear never heard it again, despite decades of searching. Theories exploded like supernova. Some argued it was a comet, but none were in the area at the time. Others suggested a military satellite or a rogue transmission bounced off space debris. But the most tantalizing possibility, that for one fleeting moment we intercepted a message not meant for us. A beacon from a civilization far older, far wiser, reaching out across the void. What chills researchers isn't just the signal itself, it's the math. The odds of a natural phenomenon mimicking those exact parameters are astronomically low. And if it was artificial, the energy required would dwarf anything humanity could produce. That's the real shock, not just that we heard something, but that whatever sent it operates on a scale we can barely comprehend. To this day, the WOW signal stands as a cosmic riddle, a fleeting glimpse into the unknown. It taught us a humbling lesson: the universe is vast, and sometimes it speaks in ways we're not yet ready to understand. When NASA Pioneer 10 and 11 spacecraft drifted beyond the edges of our solar system, they carried more than just instruments, they carried humanity's curiosity into the unknown. But by the 1990s, something impossible began unfolding. Both probes, now billions of miles from Earth, were slowing down in ways Newton's laws couldn't explain. A tiny, relentless force was tugging them back toward the sun. Not gravity as we knew it, but something subtler, stranger, Scientists called it the Pioneer Anomaly, and for over 20 years it defied every attempt at explanation. At first, researchers assumed it was a glitch, perhaps thruster fuel leaking, or heat radiating unevenly from the probe's nuclear power sources, but the math refused to cooperate. The deceleration was too precise, too constant, about 300 billionths of a centimeter per second squared. That's like a single snowflake's weight pressing against a car, yet across the vastness of space, that minuscule drag added up. It meant our understanding of physics, tested and trusted for centuries, might be missing a piece. Theories spiraled. Could it be dark matter, that invisible cosmic glue clustering near the sun in ways we'd never detected? Or evidence of extra dimensions, their gravitational pull leaking into our universe? Some even dared to whisper about modified gravity, a tweak to Einstein's relativity that would rewrite the rules of motion itself. Then, in 2012, a team of researchers cracked open Pioneer 10's decades-old blueprints. Buried in the schematics was a clue. The spacecraft's radio antennas, designed to beam data home, were also radiating heat, not uniformly but in lopsided bursts. When they modeled this effect, the numbers aligned. The anomaly wasn't a cosmic mystery, it was a quirk of engineering, photons pushing back like a faint solar wind. Yet the shock lingered. For decades, the universe had dangled a riddle that made scientists question reality itself. And in the end, the answer revealed something profound. Sometimes the deepest mysteries hide not in the void, but in the details we overlook. The Pioneer Anomaly taught us humility. Even our best tools can deceive us, and the cosmos always keeps one more secret in reserve. In October 2017, astronomers at the Pan-STARRS telescope in Hawaii spotted something streaking through our solar system that defied all expectations. At first glance, it appeared to be a comet, but this visitor wasn't from our cosmic neighborhood. Calculations revealed it had journeyed from interstellar space, the first object ever detected from beyond our solar system. They named it Oumuamua, Hawaiian for scout, a fitting title for an enigma that would challenge everything we thought we knew about celestial bodies. What made Oumuamua so shocking wasn't just its origin. Its shape was unlike anything in our solar system, a bizarre, elongated cigar, roughly 10 times as long as it was wide, tumbling end over end. Most asteroids and comets are lumpy or spherical, but Oumuamua's needle-like form was unprecedented. Then came the real curveball. As it hurtled away from the sun, it sped up slightly, as if pushed by an invisible force. Comets do this when their icy surfaces vaporize, creating a propulsive tail, but Oumuamua had no tail, no visible outgassing, no explanation. The scientific community erupted with theories. Some proposed it was a rare hydrogen iceberg, a hypothetical object that could accelerate as hydrogen sublimated in sunlight. Others suggested it might be a fragment of a shattered planet, ejected from another star system eons ago. But the most provocative idea came from Harvard astrophysicist Avi Loeb, who dared to ask, what if Oumuamua wasn't natural at all? Could its acceleration and odd shape hint at artificial origins, a solar sail or derelict probe from an alien civilization? Skeptics countered that extraordinary claims require extraordinary evidence. The truth, they argued, was likely more mundane, a peculiar but natural object behaving in ways we simply hadn't observed before. Yet even the most conservative researchers admitted one thing: Oumuamua was a wake-up call. Our telescopes had barely begun scanning the skies for interstellar visitors, and already the universe had delivered something that defied categorization. By the time Oumuamua faded from view, it had rewritten the rules. No longer could we assume all cosmic objects would fit neatly into boxes labeled comet or asteroid. Sometimes nature, or perhaps something else, throws us a mystery that refuses to be solved. Oumuamua's legacy isn't just in the questions it raised, but in the humility it imposed. The cosmos is vast, and we've only just begun to explore. Who knows what other surprises are sailing silently through the dark? In the constellation Cygnus, 1700 light-years away, a star called KSE 8462852, better known as Tabby's star, began behaving in ways that made astronomers question everything they knew about stellar physics. First detected by NASA's Kepler Space Telescope in 2009, this unassuming star should have dimmed at regular intervals like clockwork if planets orbited it. Instead, its light flickered unpredictably, sometimes dipping by just 1%, other times plunging a staggering 22%, as if something colossal was passing in front of it. Scientists expected comets or debris clouds to explain the erratic dimming, but the numbers didn't add up to block that much light. A swarm of comets would need to dwarf anything in our solar system. Enter the most sensational theory. What if this wasn't natural at all? Astronomer Jason Wright floated the idea of a Dyson swarm, a hypothetical megastructure built by an advanced civilization to harness a star's energy. The internet erupted, headlines screamed about alien superstructures, and for once, scientists didn't dismiss the hype outright. But as more data poured in, the plot thickened. The star's dips weren't symmetrical, ruling out solid objects like planets or artificial constructs. Spectroscopy revealed something else, fine dust, likely from a massive ring system or a shattered moon, scattering starlight in irregular patterns. By 2018, the leading theory pointed to an immense cloud of cosmic dust, though even that couldn't fully explain the star's extreme behavior. The shock of Tabby's star wasn't just its strangeness, it was the realization of how little we truly grasp about stellar environments. Here was a phenomenon that forced scientists to confront the limits of their knowledge, to weigh wild possibilities against Occam's razor. It reminded us that the universe doesn't owe us tidy answers. Sometimes it offers puzzles so profound they linger for years, humbling even the brightest minds. Tabby's star didn't just dim light, it dimmed our certainty, proving that the cosmos still holds mysteries we've only begun to imagine. Mars has always teased us with the possibility of life, its rusty surface hiding secrets just beneath the dust. But in 2004, the European Space Agency's Mars Express orbiter sent back data that sent shockwaves through the scientific community. Sporadic spikes of methane gas, a molecule that on Earth is overwhelmingly produced by living organisms. Here was a puzzle wrapped in red sand because methane shouldn't last long in the Martian atmosphere. Solar radiation and chemical reactions should break it apart within a few hundred years. So why was it appearing, vanishing, and reappearing like clockwork in certain regions? The implications were staggering. If the methane wasn't being continuously replenished, its presence hinted at active, ongoing sources beneath the surface. Geological processes like serpentinization, where water interacts with certain rocks, could produce methane, but so could microbes. The parallels to Earth were impossible to ignore. In our planet's darkest caves and deepest ocean vents, life thrives in conditions once thought impossible. Could Mars, with its buried aquifers and ancient hot springs, be hiding a similar secret? Then came the curveball. NASA Curiosity rover, sniffing the air in Gale Crater, detected methane levels that fluctuated wildly, sometimes 10 times higher than baseline. Even stranger, these spikes often occurred at night when atmospheric conditions should have suppressed gas release. Scientists scrambled for explanations. Was the rover itself somehow producing the gas? Unlikely. Controlled tests ruled that out. Were subsurface reservoirs leaking methane through cracks? Possibly, but no geological features matched the timing. The most electrifying possibility, that microbial life buried deep underground was exhaling methane in cycles we didn't yet understand. On Earth, certain bacteria produce methane as a byproduct of metabolism. If similar organisms existed on Mars, eking out an existence in briny pockets beneath the permafrost, their faint breath could be surfacing in these erratic bursts. Yet skepticism lingered. Mars is a planet of extremes where chemistry often defies Earth-based intuition. Volcanic activity, long thought dormant, might still simmer below the surface. Meteorites could deliver carbon-rich material that reacts unpredictably with Martian soil. Even the planet's dust storms might play a role, churning up ancient reservoirs of trapped gas. What stunned researchers wasn't just the methane itself, it was the realization of how little we know about Mars' inner workings. Every explanation raised new questions, and every detection felt like grasping at smoke. The methane spikes became a symbol of Mars' maddening elusiveness, a reminder that the red planet guards its secrets closely. Whether the source is biological or geological, one thing is certain: Mars isn't the dead world we once assumed. It's dynamic, puzzling, and perhaps, just perhaps, whispering clues about life in ways we're only beginning to hear. Somewhere in the vast cosmic tapestry, there's a patch of sky so eerily cold that it defies everything we know about the universe's infancy. Discovered in 2004 by NASA, a Wilkinson microwave anisotropy probe, this anomaly, dubbed the cold spot, stretches nearly 2 billion light-years across, a yawning void where the afterglow of the Big Bang is noticeably fainter than it should be. At first glance, it might seem like a minor irregularity in the cosmic microwave background, the faint whisper of radiation left over from the universe's fiery birth. But this isn't just a statistical blip. The cold spot's temperature is 70 microkelvin colder than its surroundings, a discrepancy so stark that the odds of it occurring by random chance are roughly 1 in 50,000. Theories flared like supernova. Could this be evidence of a parallel universe brushing against our own, as some multiverse models suggest? Or was it a colossal supervoid, a region of space so empty that light passing through it loses energy, creating a cosmic mirage? The supervoid explanation seemed plausible except for one glaring problem. When astronomers mapped the area, they found far fewer galaxies than expected, but not enough to account for the staggering temperature drop. The void wasn't void enough. It was like finding a refrigerator in the desert, its door wide open, yet still inexplicably cold inside. Then came the real curveball. In 2017, a team using the Dark Energy Survey peered deeper into the cold spot's heart, expecting to confirm the supervoid theory. Instead, they found something even stranger, a nested structure of smaller voids like bubbles within bubbles. This fractal emptiness might amplify the cooling effect, but the math still didn't quite add up. The cold spot refused to fit neatly into any cosmological box. What unsettles scientists isn't just the anomaly itself, it's the quiet challenge it poses to our most cherished theories. The standard model of cosmology, built on decades of painstaking observation, assumes the universe is broadly uniform at large scales. Yet here's a region that seems to flout those rules, a cosmic bruise that shouldn't exist. Some researchers whisper about exotic physics, dark energy fluctuating in unpredictable ways, or space-time itself warped by primordial defects left over from the universe's first moments. Others, more cautiously, suggest our instruments might be missing something, a hidden galaxy cluster, perhaps, or an unaccounted-for foreground effect. But the cold spot's greatest lesson isn't in the answers it offers. It's in the questions it forces us to confront. However this mystery resolves, it's already proven one thing: the universe, even in its oldest light, still holds surprises that rattle our understanding of reality. And that's what makes science thrilling, not the moments when everything fits, but the moments when the cosmos looks back and leaves us shivering in the cold. Deep in the cosmos, there's a phenomenon so fleeting and powerful that it can outshine an entire galaxy in the blink of an eye. Fast radio bursts, FRBs for short, are among the most baffling mysteries in modern astronomy. These bursts of radio waves last just milliseconds, yet pack as much energy as 500 million suns. The first one was discovered in 2007, buried in archival data from Australia's Parkes radio telescope. At the time, astronomers dismissed it as a glitch until more kept appearing, each one a cosmic flashbulb popping in the dark, vanishing before anyone could pinpoint its origin. What makes FRBs so shocking isn't just their intensity, it's their unpredictability. Some erupt once and never repeat. Others, like FRB 1211-2, fire off like clockwork in cycles spanning days or weeks. Then there's FRB 190520, which blasted through space with a signal so twisted by magnetic fields that scientists realized it must have passed through something extraordinarily dense, like the turbulent outskirts of a black hole. These aren't just random blips, they're fingerprints of environments so extreme they defy imagination. Theories abound, each more tantalizing than the last. Could FRBs be the death cries of neutron stars collapsing into black holes? Or perhaps starquakes on highly magnetized neutron stars called magnetars, where crustal shifts unleash tsunamis of radio waves? In 2020, astronomers got their first breakthrough when an FRB in our own galaxy was traced to a magnetar, finally linking one of these bursts to a known object. But here's the twist. Most FRBs come from billions of light years away, far beyond our galactic neighborhood. That magnetar connection explains some bursts, but not all. Then there's the elephant in the room, the possibility, however slim, that these bursts are artificial. Some FRBs repeat with patterns so precise, they've fueled speculation about alien propulsion systems or interstellar beacons. The truth, while natural explanations are far more likely, the sheer diversity of FRBs suggests we're dealing with multiple cosmic phenomena, not just one. Every new detection adds another piece to the puzzle, and sometimes it's a piece that doesn't fit at all. Perhaps the most startling lesson of FRBs is how little we understand about the universe's most energetic events. They're cosmic lightning strikes, revealing hidden corners of the cosmos where matter is stretched to its limits. With every burst, astronomers are handed a new clue and a fresh reminder that the universe is stranger, more violent, and more wondrous than we ever dreamed. Imagine the entire observable universe, every galaxy, every star, every speck of cosmic dust moving in perfect unison, as if pulled by some invisible hand beyond the edge of everything we know. That's the mystery of dark flow, a phenomenon so unsettling that even seasoned cosmologists struggle to explain it. In 2008, a team analyzing data from NASA's Wilkinson microwave anisotropy probe made an eerie discovery. Hundreds of galaxy clusters, each containing thousands of galaxies, were drifting in the same direction at speeds exceeding 2 million miles per hour. This wasn't random motion, it was a coordinated rush toward something or somewhere we can't see. At first, scientists assumed it was a statistical fluke. The cosmic microwave background, that ancient echo of the Big Bang, should be uniform in all directions. But these galaxy clusters showed telltale distortions, as if their movement left faint scratches on the fabric of spacetime itself. The shocking part, the source of this pull lies beyond the observable universe, in regions so distant their light hasn't had time to reach us in the 14 billion years since the cosmos began. Whatever's tugging these clusters defies not just observation, but the very limits of our physics. Theories collide like particles in a supercollider. One daring idea suggests the gravitational influence of another universe, brushing against ours in the multiverse's infinite tapestry. Others propose colossal structures, cosmic supervoids or domain walls, left over from the universe's birth, warping spacetime on scales we can scarcely comprehend. Skeptics counter that instrument errors or overlooked galactic dynamics might mimic the effect. Yet after years of scrutiny, dark flow persists, a ghostly current in the cosmic ocean. What chills researchers isn't just the motion itself, but what it implies. Our standard model of cosmology rests on the assumption that the universe is isotropic, uniform in all directions. Dark flow cracks that foundation. If confirmed, it means there's structure beyond our cosmic horizon, forces acting from realms we may never observe directly. It's like feeling the tides pull while stranded in a lifeboat, knowing the ocean stretches far beyond the fog. Perhaps the most profound shock is the humility dark flow forces upon us. For all our telescopes and supercomputers, the universe still holds cards it hasn't revealed. Every time we map the cosmos, it whispers back, "You're missing something." Whether the answer lies in new physics, parallel universes, or something stranger still, one thing's certain: the darkest flows often lead to the brightest revelations. For decades, astronomers faced a cosmic accounting error so glaring it threatened to rewrite the textbooks. When they tallied up all the visible matter in the universe, stars, galaxies, gas clouds, the numbers came up short. Dreadfully short. Roughly half the normal matter predicted by the Big Bang's nuclear recipes was simply missing. This wasn't dark matter, that mysterious invisible stuff. This was ordinary baryonic matter, the protons and neutrons that make up everything we can see. Scientists called it the missing baryon problem, and it gnawed at the foundations of cosmology. Where could half the universe's building blocks have gone? The breakthrough came not from peering at stars, but at the ghostly threads stretching between them. In 2017, two teams of researchers, one using the European Space Agency's XMM Newton telescope, the other NASA Chandra X-ray Observatory, finally cracked the case. They detected faint wisps of superheated gas threaded through the cosmic web, those vast filamentary structures that connect galaxies like beads on a string. This wasn't just any gas, it was searing plasma, heated to millions of degrees, so diffuse it had eluded detection for years. But when astronomers stacked observations from thousands of galaxies, the signal emerged, a reservoir of matter so colossal it accounted for every missing atom. The shock wasn't just the discovery itself, it was the realization of how obvious the solution had been in hindsight. Theoretical models had long predicted that most of the universe's ordinary matter would reside in these intergalactic highways where gravity funnels gas into sprawling rivers. But the plasma's extreme temperature made it nearly invisible to optical telescopes, while its thinness meant X-ray signals were vanishingly faint. It took cutting-edge instruments and years of painstaking data analysis to tease out the truth. What's staggering is the scale. These filaments contain enough material to build trillions of stars, yet they're so thinly spread that a cubic meter might hold just a few atoms. That's a vacuum emptier than anything we can create in labs on Earth. Yet across billions of light-years, that sparse gas adds up to the universe's hidden backbone, a revelation that reshaped our understanding of cosmic structure. But the mystery didn't end there. Researchers soon noticed something odd about this plasma. It wasn't just sitting still. Some filaments pulsed with energy, as if stirred by supermassive black holes or ancient galactic collisions. Others showed chemical fingerprints hinting at a turbulent history, where matter cycled between galaxies and the void in an endless cosmic dance. The missing baryon problem's resolution taught astronomers a humbling lesson. Sometimes the answers aren't in the bright spots, but in the shadows between them. For all our towering telescopes and supercomputers, the universe still hides its greatest treasures in plain sight, if only we know how to look. And who knows what other invisible threads woven through the darkness are waiting to be pulled. In the vast cosmic menagerie, there's a class of galaxies so ghostly, so ethereal, they've been called the invisible giants of the universe. Take Dragonfly 44, a galaxy lurking in the Coma cluster 330 million light-years away. At first glance, it's unremarkable, a faint smudge of light, barely distinguishable from the background glow of the cosmos. But when astronomers measured its mass, their instruments practically screamed in disbelief. This wispy phantom contained as much dark matter as the Milky Way, yet its stars were so sparse you could fly a spaceship through it for light years without seeing a single twinkle. The discovery of ultra-diffuse galaxies like Dragonfly 44 turned galactic evolution theories on their heads. Conventional wisdom said galaxies needed density to survive. that without enough stars huddled together, the gravitational tug of war with neighboring galaxies would tear them apart. Yet here were these cosmic ghosts floating serene and intact in some of the universe's most violent environments. Their stars were spread so thin that if you stood on a planet in one, the night sky would be nearly black, the nearest star so distant it'd appear as a dim pinprick. What shocked scientists wasn't just their existence, it was the scale of their defiance. Some ultra-diffuse galaxies, like NGC 1052DF2, took the puzzle further. They lacked dark matter entirely, appending the assumption that all galaxies are anchored by this invisible scaffold. Others, like Dragonfly 44, were 99.99% dark matter, a ratio so extreme it seemed to mock our understanding of how galaxies form. Theories ricocheted through the astronomy community. Could these galaxies be the tattered remnants of ancient collisions, their stars scattered like dust in a cosmic wind? Or perhaps failed galaxies, born in pockets of the early universe where gas was too sparse to ignite star formation? The most tantalizing idea, they might be living fossils, pristine relics from a time before supernova and black holes stirred the primordial soup of matter into the dense galaxies we know today. Every new observation deepens the mystery. Some ultra-diffuse galaxies rotate so slowly they should fly apart, yet they hold together like smoke rings that never dissipate. Others exhibit bizarre chemical compositions, their stars lacking heavy elements hinting they formed in isolation, untouched by the violent mergers that enriched most galaxies. Each discovery chips away at the neat categories we've built, proving the universe has a flair for the uncanny. What makes these ghostly galaxies so electrifying isn't just their strangeness, it's what they reveal about the limits of our knowledge. They force us to ask how many other cosmic phantoms are hiding in plain sight, camouflaged against the black, and what other rules might they be waiting to break? One of the most unsettling realizations in modern cosmology is this. Depending on how you measure it, the universe appears to be expanding at two different speeds. This isn't just some tiny discrepancy, it's a gap so glaring, so stubborn, that it sparked a crisis dubbed the Hubble tension. The problem began when astronomers tried to pin down the Hubble constant, the number that describes how fast space itself is stretching. They used two tried and true methods, studying ancient light from the early universe and measuring distances to nearby stars and galaxies. Both approaches are rock solid in their own right. Yet somehow they keep giving answers that disagree by about 10%, a margin that grows wider with every new, ultra-precise measurement. The first method relies on the cosmic microwave background, that faint afterglow of the Big Bang. By analyzing tiny temperature fluctuations in this primordial light, scientists can extrapolate how quickly the universe should be expanding today. These measurements, led by the Planck satellite, point to a Hubble constant of around 67 kilometers per second per megaparsec. But when astronomers turn to pulsating stars called Cepheid variables or cataclysmic supernova in nearby galaxies, objects whose distances and velocities we can measure directly, the number jumps to 73. That difference might sound small, but in the precise world of cosmology, it's seismic. It's like two clocks, both impeccably crafted, ticking steadily out of sync. At first, researchers assumed someone had made a mistake. Perhaps there was an unnoticed error in calibrating telescope data, or a subtle bias in how supernovae were analyzed. But as teams cross-checked their work, the discrepancy only hardened. Independent techniques, like using gravitational lensing or the echoes of colliding neutron stars, kept reinforcing the divide. The universe, it seemed, was playing a trick on us. This is where things get thrilling. The Hubble tension isn't just a math problem, it's a potential crack in the foundation of modern physics. If the measurements hold, they might imply the existence of new physics beyond the standard model. Maybe dark energy, that mysterious force accelerating the expansion, isn't constant as we thought but evolves over time. Or perhaps dark matter interacts with ordinary matter in ways we haven't accounted for. Some theorists even speculate about extra dimensions subtly warping space-time, or a fleeting, early dark energy that tweaked the universe's expansion in its infancy. What makes this moment so electric is the sheer stakes involved. The Hubble tension could be our first glimpse of something profound, a cosmic anomaly hinting at forces or particles we've never dreamed of. Or, as skeptics caution, it might simply reveal an overlooked systematic error in our observations. Either way, the tension has ignited a feverish race to settle the debate, with next-generation telescopes like the James Webb Space Telescope and the Vera Rubin Observatory poised to deliver answers. The Hubble tension teaches us something beautiful about science. It's in these moments of discord, when nature refuses to follow the script, that the most groundbreaking discoveries are born. Whether the solution points to revolutionary physics or humbler corrections, one thing is certain: the universe still has surprises up its sleeve, and we're only beginning to unravel them. In February 2017, astronomers turned their telescopes toward a dim, cool star 40 light-years away, and found a planetary lineup so shocking it shattered every expectation about how solar systems form. TRAPPIST-1, an ultra-cool dwarf star barely larger than Jupiter, wasn't supposed to host planets at all, let alone 7 of them, each roughly Earth-sized, each dancing in a delicate gravitational harmony that defied the chaos of most known systems. The first clue came in 2015, when the TRAPPIST telescope in Chile spotted subtle dips in the star's light, telltale signs of planets passing in front of it. But nothing prepared scientists for the follow-up observations. NASA's Spitzer Space Telescope revealed not 1 or 2, but 7 worlds crammed into a space smaller than Mercury's orbit around our Sun. Imagine squeezing our entire inner solar system into a region 1/5 its size, with planets so close together that standing on one, you could see neighboring worlds looming in the sky, their geological features visible to the naked eye. What made this discovery revolutionary wasn't just the number of planets, it was their potential. 3 of them orbit in the star's habitable zone, that Goldilocks region where liquid water could pool on the surface. But here's the twist: TRAPPIST-1 habitable zone is 20 times closer to its star than Earth is to the Sun, bathing these worlds in perpetual twilight. The star emits mostly infrared light, giving its planets an eerie, deep red glow like perpetual sunset. Yet because the star is so cool, they might still be temperate, with atmospheres that redistribute heat evenly across their surfaces. The real shock came when researchers modeled the system's stability. 7 planets orbiting this close should have collapsed into each other eons ago. Instead, they're locked in a complex gravitational waltz called a resonance chain, their orbits synchronized so precisely that for every 2 revolutions one planet makes, the next completes 3, creating a rhythm that keeps the system stable. It's as if the universe composed a celestial symphony, each world an instrument playing in perfect time. But the burning question remains: could any of these planets harbor life? TRAPPIST-1 worlds are likely tidally locked, with one side perpetually facing the star and the other in eternal night. That could create wild climate extremes, scorching deserts on one hemisphere, frozen wastelands on the other. Yet in the twilight band between these zones, conditions might be just right for liquid water. Even more intriguing, these planets are so close that atmospheric molecules could hop between them via solar winds, potentially seeding life across multiple worlds. The implications are staggering. Before TRAPPIST-1, no one imagined a single star could host so many Earth-sized planets, let alone in such precarious balance. It forced astronomers to reconsider how common habitable worlds might be, especially around red dwarfs, which make up 75% of all stars in the galaxy. Suddenly, the cosmos seemed richer, stranger, more generous with its real estate. Yet mysteries linger. Recent studies suggest some TRAPPIST-1 planets might have thick, Venus-like atmospheres, while others could be stripped bare by stellar flares. The James Webb Space Telescope is now peering at their atmospheres, hunting for signs of water vapor, oxygen, or even industrial pollutants, hints of a civilization. Whatever it finds, the TRAPPIST-1 system has already rewritten the rules. It taught us that planetary systems can thrive in configurations we never dreamed possible, and that the search for life might not be a quest for a second Earth but a seventh. In the constellation Aquarius, there was once a star so massive, so brilliant, it should have gone out with a bang heard across the cosmos. Designated N694, this blue supergiant was 25 times heavier than our Sun, the type of star destined for a spectacular supernova death. Astronomers had been watching it for decades, waiting for the inevitable explosion. Then, in 2009, something impossible happened. N694 didn't explode, it simply vanished. No fiery blast, no glowing remnant, not even a whisper of the neutrinos that always accompany a star's collapse. One moment it was there, shining defiantly against the black. The next it was gone without a trace. The discovery sent shockwaves through astrophysics. Stars this massive don't just disappear. They die violently, scattering their guts across space in explosions that outshine entire galaxies. Yet when researchers scoured archival images from the Hubble Space Telescope, they found only darkness where N694 had once burned, the leading theory. This star might have skipped the supernova stage entirely, collapsing straight into a black hole, a phenomenon so rare it had only existed in theory until now. But here's where the mystery deepens. Normally, when a massive star collapses into a black hole, there's still a visible aftermath, a burst of energy as the outer layers rebound off the newborn singularity. N694 showed nothing. It was as if the star had been yanked off the cosmic stage by some invisible hand. Scientists scrambled for explanations. Could it have imploded into a black hole so quickly that the explosion was smothered in the act? Or might it have been shrouded by a thick veil of dust, hiding its death throes from our telescopes? The most tantalizing possibility is that N694 represents an entirely new way for stars to die. Some models suggest supermassive stars might occasionally undergo a failed supernova, where their cores collapse so abruptly that the outer layers fall inward too fast to ignite a proper explosion. Instead of lighting up the cosmos, the star effectively swallows its own death, a cosmic disappearing act. What unsettles astronomers isn't just the star's silence. It's the chilling implication that this might not be as rare as we think. If massive stars can vanish without warning, how many others have we missed? The universe, it seems, has a way of keeping its most dramatic exits quiet. N694's eerie vanishing act forces us to reconsider the life cycles of stars and reminds us that even in death, the cosmos keeps its secrets close. In 2010, NASA's Fermi Gamma Ray Space Telescope unveiled a cosmic spectacle no one saw coming. Two colossal bubbles of searing hot gas, each stretching 25,000 light-years from the Milky Way's core, towering above and below our galaxy like a titanic hourglass. These weren't just any structures, they were blazing with gamma rays, the most energetic light in the universe, and they dwarfed anything else in our galactic neighborhood. The discovery sent shockwaves through astrophysics because these Fermi bubbles shouldn't have been there, at least not according to any existing model of galactic behavior. What makes these bubbles so baffling isn't just their size, it's their defiance of time and physics. The gas inside them is scorching at millions of degrees, yet there's no obvious source of heat. One leading theory points to Sagittarius A, the supermassive black hole at our galaxy's heart, suggesting it might have had a violent feeding frenzy in the past, devouring enormous amounts of matter and belching out jets of energy that inflated these bubbles like cosmic balloons. But here's the twist. If that's true, the eruption would have had to be staggeringly powerful, a blast equivalent to 100 stars converting their entire mass into pure energy. And yet, there's no record of such an cataclysm in the Milky Way's otherwise orderly history. Then there's the dark matter angle. Some researchers speculate these bubbles could be the aftermath of annihilating dark matter particles colliding near the galactic center, releasing bursts of gamma rays as they destroy each other. It's a tantalizing idea, except we've never detected dark matter behaving this way anywhere else in the universe. The bubble's sharp edges add another layer of intrigue. Unlike the diffuse halos seen around other galaxies, the Fermi bubbles have crisp boundaries, as if something or someone sculpted them with precision. Perhaps the most unsettling realization is how recently we spotted them. These structures loom over our own galaxy, visible across half the night sky if you could see gamma rays, yet they went unnoticed until the 21st century. It's a humbling reminder that even in our cosmic backyard, the universe still harbors giants hiding in plain sight. The Fermi bubbles aren't just relics of some ancient explosion, they're a live puzzle, challenging us to rethink how galaxies evolve, how black holes shape their surroundings, and what other invisible forces might be at work in the darkness above our heads. Every new observation peels back another layer, but the truth remains elusive. Sometimes the most shocking discoveries aren't just about what we find, they're about what we've been missing all along. About 40 light-years from Earth, orbiting a sun-like star in the constellation Cancer, there's a world that makes even the most extravagant sci-fi fantasies seem tame. Meet 55 Cancri E, a planet twice the size of Earth, but with a composition so bizarre it left astronomers speechless when they first unraveled its secrets. Initial observations suggested this wasn't just another rocky exoplanet. The numbers told a story of a world so carbon-rich, so compressed by gravity that a third of its mass literally could be diamond. Not scattered gems buried beneath the surface, but a vast, glittering mantle spanning thousands of miles, with the crushing pressure of a stellar forge turning carbon into the hardest substance known. The discovery sent shockwaves through planetary science because 55 Cancri E shouldn't exist, at least not according to conventional models. Our solar system is dominated by oxygen-rich worlds where carbon is a trace element. But here was a planet where carbon might outweigh oxygen, a scenario so extreme it forced scientists to reconsider how planetary systems form, the leading theory. Its host star, 55 Cancri A, is unusually carbon-rich, seeding its protoplanetary disk with the raw materials for diamond worlds. In this cosmic refinery, carbon atoms squeezed under pressures 1,000,000 times greater than Earth's atmosphere could have crystallized into a diamond lattice hundreds of miles thick. But the surprises didn't stop there. Further studies revealed 55 Cancri E is a world of extremes, locked in a death grip with its star. It orbits so close, 17 times nearer than Mercury is to our Sun, that a year lasts just 18 hours. Surface temperatures soar above 4,000 degrees Fahrenheit, hot enough to vaporize rock and turn any exposed diamond layers into a shimmering, molten sea. Some models even suggest the planet's dayside is permanently molten, while its night side might harbor solid diamond plateaus glowing red-hot under a sky of carbon monoxide. The real twist came when astronomers analyzed its atmosphere. Instead of the expected hydrogen or helium, they detected traces of hydrogen cyanide, a toxic gas that, under the right conditions, could react with the planet's carbon to form even more diamond. It's a hellish vision, a world where hydrocarbon rains might literally crystallize into diamond hailstones midair, only to melt again before hitting the surface. What stunned researchers most wasn't just the planet's opulence, it was the realization of how little we understand about planetary diversity. 55 Cancri E proved that the universe crafts worlds from recipes we've never dared imagine. It's a laboratory of extremes where chemistry bends to forces we can barely replicate on Earth, and where the line between mineralogy and alchemy blurs into obsolescence. Yet the diamond planet's greatest lesson isn't about wealth, it's about perspective. For all its glittering allure, 55 Cancri is a monument to cosmic violence, a reminder that the universe doesn't just create life-friendly oases. Sometimes it forges jewels in the crucible of catastrophe, spinning beauty from the very forces that would obliterate us. And who knows, somewhere out there, another world might be waiting to shatter our assumptions all over again. Deep in the cosmic void, astronomers recently stumbled upon something that shouldn't exist: colossal, perfectly circular rings of radio energy, so vast they could swallow entire galaxies. Dubbed odd radio circles or ORC, these enigmatic structures span a staggering million light-years across, etched into the fabric of space like ripples from a stone thrown into a pond. But here's the catch: no stone was ever thrown. No explosion, no collision, no known cosmic event could explain rings so symmetrical, so pristine, they seemed almost designed. The first ORC was spotted in 2020 by Australia's ASCAP radio telescope, a facility designed to map the universe's faintest whispers. What began as a routine scan quickly turned into a feverish mystery. The rings weren't tied to any visible object, no galaxy at their center, no cluster of stars. They simply hung in space, glowing faintly in radio waves but invisible to optical telescopes. It was like finding a smoldering campfire ring in a forest, only to realize there'd never been a fire. Theories erupted, each more speculative than the last. Perhaps these were shock waves from gargantuan black hole mergers, though no such event had been recorded nearby. Others suggested they might be the ghosts of quasar tsunamis, where dying quasars blast out spherical shells of energy. But the most tantalizing and unsettling idea was that ORCs could be the throats of wormholes, their immense gravitational lenses bending light into perfect circles. What truly stunned scientists was the sheer precision of the rings. Natural cosmic phenomena tend to be messy: explosions leave jagged debris, collisions scatter matter unevenly. Yet these ORCs were geometric marvels, their edges razor-sharp, their shapes unbroken. Even stranger, some ORCs contained galaxies inside their rings, like flies trapped in amber, but the galaxies showed no signs of disturbance. It was as if the rings had formed around them without touching them, a cosmic magic trick with no visible sleight of hand. As more ORCs were discovered, the puzzle deepened. Some floated in isolation, others appeared in clusters. A few even had faint, concentric rings nested inside them, like tree rings marking unseen epochs of cosmic time. The only common thread: they existed exclusively in radio wavelengths, silent to all other forms of observation. It's as if the universe had switched on a neon sign written in a language we're only beginning to decipher. The discovery of ORCs forces a humbling admission. Even with our most advanced tools, we're still missing entire chapters of cosmic physics. These rings could be the fingerprints of phenomena we've never imagined, echoes of higher dimensions, artifacts from before the Big Bang, or even markers of civilizations so advanced they've reshaped spacetime itself. While the truth remains hidden, one thing is certain: the universe loves a good mystery, and ORCs are its latest, most elegant enigma. In the depths of the cosmos, astronomers recently found a black hole so monstrous it ripped apart the rulebook of astrophysics. Lurking in a galaxy 15,000 light-years away, this gravitational behemoth, dubbed LB1, tips the scales at 70 times the mass of our Sun. Here's the jaw-dropper: according to everything we know about stellar evolution, black holes this heavy simply shouldn't exist in our corner of the universe. The discovery sent shockwaves through the scientific community, igniting a firestorm of debate about how stars live, die, and collapse into the darkest corners of spacetime. The problem starts with a fundamental limit. When massive stars exhaust their nuclear fuel, their cores implode under gravity's crush, triggering supernova that blast away their outer layers. What remains should theoretically max out around 50 solar masses. Any heavier, and the resulting explosion would be so violent it would obliterate the collapsing core entirely. Yet LB1 defies this ceiling with brazen indifference, leaving astronomers scrambling for explanations. Could it be the product of two smaller black holes merging in secret? Or perhaps a relic from the ancient universe where stars grew to sizes we've never witnessed? The plot thickened when researchers scrutinized LB1's companion, a massive blue star orbiting it in a cosmic dance. The star's composition held a clue. It was rich in helium but stripped of hydrogen, suggesting it had once been part of a binary system where its twin collapsed into the black hole. But here's the twist. For LB1 to reach its current mass, the original star would have needed to weigh over 100 suns. Stars that colossal are supposed to end their lives as pair instability supernova, annihilating themselves so completely they leave no black hole behind. LB1 shouldn't just challenge the rules, it should have erased them. Theories erupted like supernova. Some proposed that LB1 formed not from a single star's death, but from a cascading merger of multiple black holes over eons. Others speculated about fallback supernova, where dying stars partially explode but then suck some of the ejected material back into the abyss, bulking up the final black hole. The most radical idea, that LB1 is a primordial black hole forged in the chaos of the Big Bang itself, a time when the universe's density could have birthed such monsters naturally. Yet even these explanations strain credibility. Mergers should produce observable gravitational waves, but none match LB1's timeline. Primordial black holes remain hypothetical, with no direct evidence they exist. And fallback scenarios struggle to account for the sheer scale of this anomaly. The silence from conventional models is deafening, a reminder that the cosmos often reserves its most shocking revelations for the moments we least expect them. What makes LB1 truly transformative isn't just its existence, it's the humility it demands. For decades, our understanding of black holes has been anchored by tidy equations and well-tested limits. Now, staring into the void of this gravitational paradox, we're forced to admit the universe doesn't play by our rules, it drafts its own. Whether LB1 is a cosmic fluke or the first of many rule breakers waiting to be found, one thing's certain: the story of stellar death is far from written. And somewhere out there, another black hole might be lurking, ready to rewrite the next chapter. Venus has always been the solar system's cautionary tale, a scorching, toxic world where lead melts on the surface and sulfuric acid rains from the skies. But in September 2020, this planetary hellscape delivered a shock that made scientists question everything they thought they knew about the limits of life. A team of astronomers using the James Clerk Maxwell Telescope in Hawaii and the Oumuamua Array in Chile detected traces of phosphine, a gas that, on Earth, is almost exclusively produced by microbes thriving in oxygen-free environments floating in Venus's upper clouds. The discovery sent seismic ripples through the scientific community because, according to every known non-biological process, phosphine shouldn't exist there. Volcanoes can't make it in sufficient quantities, lightning doesn't produce it, even meteorites deliver negligible amounts, yet the signal was unmistakable: 20 parts per billion of a molecule that had no business lingering in Venus's atmosphere. The implications were staggering. If not geology or chemistry, what or who was creating it? On Earth, phosphine is a calling card of anaerobic bacteria, organisms that thrive in swamps, sewers, and the guts of animals. Finding it on Venus raised an electrifying possibility. Could microbial life be floating 50 kilometers above the surface, sheltered in temperate cloud layers where temperatures and pressures mirror Earth? These hypothetical Venusian microbes wouldn't resemble anything familiar. They'd need to endure constant sulfuric acid baths and extract energy from trace atmospheric chemicals. But extremophiles on Earth have proven life can adapt to the unlikeliest niches. Why not the clouds of Venus? The backlash was swift and fierce. Skeptics pointed to potential data artifacts, maybe the telescopes had misread sulfur dioxide, a common Venusian gas, as phosphine. Others argued that unknown geochemical processes peculiar to Venus's hostile environment might explain the detection. When NASA and independent teams reanalyzed the data, some failed to replicate the results entirely, igniting a fiery debate about observational techniques and statistical significance. The scientific method was working as intended, but the uncertainty only deepened the mystery. Then came another twist. A 2021 study proposed that volcanic activity, if far more intense than currently estimated, might produce trace phosphine. But Venus's volcanoes, while numerous, show no evidence of such apocalyptic eruptive power. The numbers simply didn't add up unless we'd fundamentally misunderstood Venus's geology. Meanwhile, astrobiologists countered with models showing how hypothetical microbes could cycle phosphorus in Venus's clouds, creating a self-sustaining phosphine loop. The debate crystallized a profound question. When you eliminate every known explanation, do you accept an unknown chemical process or dare to consider biology? What made this moment unforgettable wasn't just the phosphine itself, it was the cultural tremor it triggered. For decades, the search for extraterrestrial life had focused on Mars and icy moons. Suddenly, Venus, of all places, demanded a second look. Space agencies scrambled to propose missions, from balloon-borne cloud samplers to orbiters with phosphine-specific sensors. The discovery became a rallying cry for revisiting our twisted sister planet, a reminder that life, if it exists, might not play by our expectations. Whether the phosphine signal holds or fades under further scrutiny, its legacy is secure. It forced us to confront our biases about where life can thrive and rewrote the narrative of Venus from a dead world to a potential cosmic oasis, albeit one cloaked in acid and mystery. Sometimes the most shocking discoveries aren't about finding answers, but realizing how many questions we've failed to ask. Deep beneath the ice of Antarctica, an array of sensors buried in a cubic kilometer of pristine frost lies in wait, not for light, not for sound, but for the most elusive travelers in the cosmos. On September 22, 2017, these detectors at the Ice Cube Neutrino Observatory caught something extraordinary. A single, high-energy neutrino streaking through the Earth, carrying with it a message from one of the universe's most violent places. What made this ghostly particle so shocking wasn't just its energy, enough to power a small city for a second, but where it came from. Tracing its path backward led scientists to a blazar 4 billion light-years away, a supermassive black hole spewing jets of radiation directly toward Earth. For the first time in history, we'd pinpointed the cosmic birthplace of a neutrino. Neutrinos are the universe's ultimate ghosts, subatomic particles so indifferent to matter that trillions pass through your body every second without a single interaction. They're born in the heart of stars, the fury of supernova, and the cataclysmic collisions of black holes, racing across space at nearly the speed of light, untouched by magnetic fields, undeterred by planets or stars. Catching one is like trapping smoke with your bare hands. Yet this particular neutrino, dubbed Ice Cube 170322A, carried an energy of 290 tera-electronvolts, 40 times more powerful than anything the Large Hadron Collider can produce. When telescopes swiveled to its origin, they found TXS 0506 plus 056, a blazar whose jet was in the throes of an apocalyptic outburst. The implications were staggering. We'd just unlocked a new way to see the universe. What stunned researchers wasn't just the detection, it was the partnership that made it possible. Neutrino astronomy had always been a solo act, studying particles in isolation. But by combining Ice Cube's deep freeze detectors with traditional telescopes, scientists achieved something revolutionary: multi-messenger astronomy. For decades, we'd relied on light alone to decode the cosmos. Now, by adding neutrinos and later gravitational waves, we could piece together cosmic events like never before. It's the difference between watching a silent film and hearing the soundtrack. Suddenly, the universe had a voice. The Blazar connection raised even thornier questions. How exactly do black holes accelerate particles to such insane energies? Some theories suggest magnetic fields near the black hole's event whip protons to near light speeds, where they collide with photons, spawning neutrinos as a byproduct. Others posit that shock waves in the jet itself act as cosmic particle accelerators. But the math remains messy. Our models can't yet fully explain the sheer violence required to produce neutrinos this potent. Then there's the eerie efficiency of it all. Neutrinos barely interact with anything, yet they travel billions of light years without losing energy, arriving at Earth as pristine cosmic telegrams. Compare that to light, which gets scattered, absorbed, or distorted by dust and gas along the way. Neutrinos are the universe's perfect messengers, if only we can learn to read them. IceCube's detection proved these ghost particles could guide us to phenomena invisible to conventional telescopes, like black holes hidden behind thick dust clouds, or the engines of distant galaxies veiled by their own brilliance. Perhaps the most electrifying possibility is what this means for the search for dark matter. Some theories suggest certain dark matter particles, when they decay or collide, could produce high-energy neutrinos. If so, every neutrino we trace might be a breadcrumb leading us closer to solving one of cosmology's greatest riddles. The Blazar discovery was just the beginning, a proof of concept that neutrinos can be cosmic roadmaps, pointing us to the universe's most secretive arenas of destruction and creation. What makes this moment so transformative isn't just the science, it's the shift in perspective. For centuries, astronomy was bound by the limits of light. Now, with neutrinos, we're learning to see through the darkness. Every ghost particle that reaches us is a crack in the cosmic code, a whisper from realms where the universe writes its most violent poetry in particles we're only beginning to understand. And somewhere out there, another neutrino is racing toward us, carrying secrets we haven't even thought to ask about yet. Most maps of the universe show a glittering tapestry of galaxies clustered like cities in the night. But in the constellation Boötes, there's a hole in the cosmic canvas so vast, so unnervingly empty, it defies logic. Stretching 330 million light-years across, the Boötes Void isn't just a gap, it's a cosmic desert so barren, you could fling the Milky Way into it and its nearest galactic neighbor would still be millions of light-years away. Discovered in the 1980s by astronomer Robert Kirshner, this yawning abyss holds just 60 galaxies where there should be thousands, a haunting emptiness that challenges everything we thought we knew about the structure of the universe. What makes the Boötes Void so unsettling isn't just its size, it's the sheer improbability of its existence. According to the standard model of cosmology, matter should be distributed relatively evenly across the universe, with galaxies congregating in web-like filaments separated by modest voids. But the Boötes Void flips that assumption on its head. Imagine stirring a spoonful of glitter into a bathtub of water, then finding a corner where not a single speck floats. That's the level of statistical absurdity we're dealing with. The odds of nature carving out a void this colossal are roughly 1 in a million, forcing scientists to confront an uncomfortable question. Did something erase this region of space, or are we missing a fundamental law of physics? Theories range from the speculative to the spine-tingling. Some suggest the void could be the scar of an ancient collision between our universe and another bubble universe in the multiverse. A cosmic crash so violent it cleared out everything in its path. Others propose it's the footprint of a super-advanced civilization that somehow harnessed dark energy to push galaxies away, though even the most optimistic SETI researchers admit that's a stretch. The leading hypothesis, however, points to a phenomenon called Baryon acoustic oscillations, a sound waves from the Big Bang that might have stretched certain regions into unnatural emptiness. But even that explanation leaves gaps. The void's edges are too sharp, its interior too vacant, as if the universe left this patch deliberately blank. Then there's the eerie silence. Galaxies within the Boötes Void aren't just sparse, they're isolated, cut off from the usual streams of cosmic gas that fuel star formation. Many appear old and dormant, their stellar nurseries long since shut down. It's as if time moves differently there, a pocket of the cosmos frozen in a state of quiet decay. Astronomers call these red and dead galaxies. Their once vibrant spiral arms faded into ruddy ghosts. If the universe has a retirement home, this might be it. Yet the void's greatest shock might be what it reveals about our place in the cosmos. For centuries, we've assumed the universe is homogeneous, that no matter where you look, the same rules apply. The Boötes Void whispers otherwise. It's a reminder that even on scales beyond human comprehension, the universe can still produce outliers so extreme they force us to rewrite the textbooks. Whether it's a statistical fluke, a sign of new physics, or something stranger still, one thing's certain: the cosmos loves a good mystery, and the Boötes Void might be its most unnerving riddle yet. Tabby's star refuses to fade quietly into the cosmic background. Years after its bizarre flickering sparked wild theories about alien megastructures, new observations have peeled back another layer, but instead of solving the puzzle, they've revealed just how much we still don't understand. Follow-up studies with NASA's Spitzer and Hubble telescopes confirmed that the star's erratic dimming wasn't caused by a monolithic Dyson swarm after all, but by something far more elusive: microscopic dust. Not the uniform clouds we're used to, though. This dust behaves unlike any seen in our solar system: clumpy, uneven, and orbiting the star in ways that make no sense. The real shock came when astronomers analyzed the dust's composition. Unlike the icy grains found around young stars or the silicate particles common in planetary debris disks, Tabby's star seems shrouded in something far stranger. Particles so fine they're more like smoke than sand, filtering the star's light asymmetrically. Some wavelengths dim dramatically while others pass through unscathed, as if the dust itself is selectively hiding parts of the star's spectrum. Even more baffling, the dust clouds aren't static. They shift over time, sometimes thickening, sometimes vanishing entirely, as if choreographed by some unseen force. Then there's the timing. Early data suggested the dimming events occurred at semi-regular intervals, sparking hope for a predictable pattern, but newer observations shattered that illusion. The star now dims erratically, once by 22% over just days, then barely flickering for months. It's as if whatever's obscuring the star has a mind of its own. Some researchers speculate about a massive asteroid collision, its debris still swirling in chaotic orbits. Others point to a family of comets trapped in gravitational resonance, though no known comet swarm could explain the dust's sheer quantity or its spectral fingerprints. The most tantalizing clue lies in the star's long-term fading. Over the past century, Tabby's star has dimmed by nearly 15% overall, a slow, inexorable darkening with no clear cause. Dust alone can't explain this. It should either dissipate or accumulate uniformly, not create a gradual, century-long decline. Could it be the aftermath of a cataclysmic event, like a swallowed planet or a nearby supernova shockwave? Or is this the signature of something even rarer, a star in the throes of an unprecedented phase shift, rewriting the rules of stellar aging? What makes Tabby's star so endlessly compelling isn't the answers we've found, but the questions that keep multiplying. Every time we think we've pinned it down, it throws another curveball. It's a cosmic reminder that the universe doesn't owe us neat explanations sometimes. It serves up mysteries that blur the line between the impossible and the inevitable. And somewhere in that flickering light, there's a lesson we're still learning. The most shocking discoveries aren't the ones that fit our models, but the ones that shatter them. In March 2016, a faint but unmistakable signal began repeating from a galaxy 3 billion light-years away, a signal that would crack open one of astronomy's most perplexing mysteries while deepening another. Fast radio bursts had always been cosmic will-o'-the-wisps, appearing once and vanishing into the void. But this one, FRB 1211-2, did something unprecedented. It flashed again. And again and again. The detection sent shockwaves through astrophysics, not just because it repeated, but because scientists finally pinpointed its origin, a tiny, unassuming dwarf galaxy pulsing with star formation. The localization was a triumph of cosmic detective work. Using the Very Large Array in New Mexico and the European VLBI network, astronomers narrowed the source to a region just 100 light-years across, a pinprick in the cosmic vastness. But the real shock came when they examined the host galaxy. This wasn't the grand spiral or massive elliptical they'd expected. It was a modest, gas-rich dwarf, the kind of place where stars are born in chaotic bursts. The implications were staggering. Whatever produced these bursts wasn't tied to the galaxy's overall size or maturity, but to something far more specific and far more enigmatic. Then came the curveball. FRB 1211-2 wasn't just repeating, it was cycling. Over months of observation, scientists realized its outbursts followed a rough pattern. Weeks of frenzied activity, then months of eerie silence. This wasn't random chaos, it was a cosmic metronome ticking on a scale we couldn't yet decipher. Theories erupted like supernova. Could this be a neutron star wobbling precariously near a black hole, its magnetic field snapping under strain? Or perhaps a magnetar, one of the universe's most magnetic objects, undergoing periodic seismic tantrums that sent shockwaves through its surroundings? The most tantalizing clue lay in the bursts themselves. Unlike one-off FRBs which blast their energy in a single millisecond, this repeater's emissions sometimes flickered with substructure tiny pulses within pulses, like a stuttering cosmic lighthouse. That intricate structure suggested an engine of astonishing complexity, something capable of producing not just raw energy but finely tuned radio symphonies. Yet for every answer, a dozen new questions sprouted. Why did some repeating bursts arrive with a slight delay, as if echoing through some invisible medium? Why did the signal's polarization twist as it traveled, hinting at magnetic fields far stronger than anything in our galaxy? And most baffling of all, why did this tiny, unremarkable galaxy host something so extraordinary? What makes FRB 1211-2 so transformative isn't just the mystery it embodies, it's the door it kicked open. By proving FRBs could repeat, it forced scientists to rethink their catalog. Were one-off bursts and repeaters two sides of the same coin, or entirely different phenomena? Could some of the singular bursts we dismissed as cosmic accidents actually be repeaters on a slower, subtler schedule? The repeater's greatest gift was humility. It reminded us that the cosmos doesn't reveal its secrets all at once. Sometimes it whispers, in bursts of radio waves, in cycles of silence, in the quiet persistence of a signal that refuses to fade. And somewhere out there, another FRB is waiting, ready to rewrite the rules all over again. Deep in the cosmic shadows, astronomers have stumbled upon a ghost, a galaxy so faint it barely exists. Designated J062145, this cosmic specter drifts through the Coma cluster nearly 330 million light-years away, a place where the rules of galactic formation seem to have been rewritten. At first glance, it's nothing more than a wisp of light, a smear against the black. But when scientists measured its mass, the numbers defied logic. This gauzy phantom weighed as much as the Milky Way, yet it held almost no stars, just a handful of ancient, flickering embers scattered across an unfathomable void. The rest invisible, unseen. The galaxy, it turned out, was made almost entirely of dark matter. This wasn't just another oddball in the menagerie of cosmic curiosities. The discovery of a dark galaxy forced astronomers to confront a question that still echoes through conference halls. How does something so massive form without lighting up the sky? Traditional models suggest galaxies begin as clouds of gas, collapsing under gravity until stars ignite, painting the darkness with light. But J062145 skipped the fireworks. Its dark matter halo, that invisible scaffold thought to seed all galaxies, never gathered enough gas to spark stellar birth. Or perhaps something stripped it away, leaving behind a cosmic husk, a galaxy that never truly lived. The implications are profound. If dark galaxies are common, they'd be the universe's silent majority, lurking undetected unless they drift in front of brighter objects. Some researchers speculate they could solve the missing satellite problem, a decades-old puzzle where simulations predict thousands of dwarf galaxies orbiting large ones like the Milky Way, yet we've found only a fraction. Could these invisible halos be the missing pieces, their starless forms hiding in plain sight? Then there's the eerie quiet. Without stars, dark galaxies lack the winds and explosions that stir ordinary galaxies, leaving their dark matter undisturbed in near-perfect halos. That purity makes them ideal laboratories for studying dark matter's nature. If we can find them, their discovery hinges on gravitational lensing, where their mass bends light from objects behind them like a cosmic magnifying glass. But even then, they're phantoms, leaving only subtle warps in spacetime as evidence. The most unsettling possibility, J062145, might not be alone. Some theorists suggest entire dark galaxies could orbit our own, their gravitational tugs subtly nudging visible stars. Others propose they're remnants of the early universe, primordial pockets where matter never ignited. Whatever the truth, their existence forces us to reconsider how galaxies are born, and how many more shadows might be watching silently from the dark. What lingers isn't just the mystery of these starless giants, but the humility they impose. For centuries, we've mapped the cosmos by the light it emits. Now we're learning to read the darkness and finding it's far from empty. The moon has always been a world of stark contrasts, brilliant sunlight and pitch-black shadows, freezing nights and scorching days. But beneath its cratered surface lies a hidden network so vast, it rewrote our understanding of lunar geology. Sprawling lava tubes carved by ancient rivers of molten rock, now frozen into tunnels large enough to swallow entire city blocks. When Japan's Selene orbiter and NAS, a lunar reconnaissance orbiter, first mapped these subterranean labyrinths in the late 2010s, the data stunned scientists. These weren't just narrow cracks, some stretched for dozens of miles, with ceilings soaring hundreds of feet high, and chambers so voluminous they could shield whole colonies from the moon's deadly extremes. What makes these tunnels so shocking isn't just their size, it's their perfection. On Earth, lava tubes collapse under gravity and weather, leaving broken husks. But the moon, with its weaker gravity and no atmosphere, preserved these conduits like cosmic time capsules. Radar scans revealed some tunnels still intact after billions of years, their floors smooth and ceilings arched like cathedral vaults. The largest, discovered near the Marius Hills, could comfortably house a metropolis, a ready-made habitat shielded from meteorites, solar radiation, and temperature swings that range from 270 degrees below zero to 260 above. Suddenly, the dream of lunar bases shifted from sci-fi fantasy to tangible blueprint. Why bury habitats under tons of regolith when nature had already built the ideal shelters? These tubes offer more than protection, they're treasure troves of scientific opportunity. Their walls might hold pristine volcanic records from the moon's fiery youth, while shaded recesses could trap water ice, a priceless resource for life support and fuel. Some researchers even speculate about microbial life hibernating in these dark recesses, though that remains a leap. Yet the real surprise came when scientists realized these tunnels weren't unique to the moon. Mars, Mercury, and even asteroids show signs of similar formations, hinting at a universal phase of subterranean architecture across the solar system. The discovery forced a humbling admission. We'd spent centuries staring at planetary surfaces while the real frontiers lurked beneath our feet. Now, as agencies plan lunar settlements, these tunnels are prime real estate, not just for survival, but for unraveling the moon's violent past. Future missions might send spelunking robots to map their depths, or even inflatable habitats to stake humanity's first permanent claim in the underworld of another world. The lesson: sometimes the greatest discoveries aren't in the light, but in the shadows we never thought to explore. In the deepest reaches of space and time, where telescopes glimpse the universe in its infancy, astronomers recently uncovered a paradox that upended everything we thought we knew about cosmic chemistry. When the James Webb Space Telescope turned its golden eye toward galaxies born just 500 million years after the Big Bang, mere toddlers in cosmic terms, it detected something impossible: oxygen. Not just trace amounts, but concentrations rivaling modern galaxies. This wasn't supposed to happen. According to decades of astrophysical theory, these early galaxies should have been barren, their stars too young to forge heavy elements through nuclear fusion. Yet there it was, the spectral fingerprint of oxygen, clear as a cosmic scream, written in light that had traveled 13 billion years to reach us. The discovery sent shockwaves through astrophysics because oxygen isn't just another element, it's a clock. It takes generations of stars living, dying, and exploding to seed the universe with significant amounts. Massive stars fuse hydrogen into helium, then carbon, and finally oxygen in their cores over millions of years. When these stars go supernova, they scatter these elements into space. For oxygen to appear so early, either the first stars formed and died at breakneck speed, or our models of stellar evolution are missing something fundamental. The most shocking possibility: that the universe's chemical enrichment didn't happen gradually, but in sudden, violent bursts we've never witnessed. Then came the twist. Webb's data revealed this ancient oxygen wasn't uniformly distributed, it clustered in pockets, as if concentrated by some unseen force. Some galaxies showed oxygen levels comparable to the Sun, while neighboring ones remained nearly pristine. This patchiness defies expectations. In modern galaxies, supernova and stellar winds mix elements evenly over time. But these early galaxies seem to harbor oxygen oases, regions where enrichment happened at staggering speed. One theory suggests supermassive stars, hundreds of times heavier than our Sun, might have dominated the early cosmos. These behemoths would have burned bright and died young, peppering space with heavy elements in just a few million years. The catch: we've never observed such stars directly. They exist only in theoretical models. The implications ripple far beyond chemistry. Oxygen is a building block of water, organic molecules, and ultimately life as we know it. If it existed in abundance so early, the timeline for habitable worlds may stretch back much further than we imagined. Imagine planets forming around these ancient stars, their atmospheres already rich with the ingredients for oceans and air. It's a radical thought that life's cosmic window might have opened barely a cosmic heartbeat after the Big Bang. Yet the mystery deepens. Some of these oxygen-rich galaxies are bizarrely compact, cramming star formation into regions a fraction the size of the Milky Way. This intensity could explain rapid enrichment supernova detonating in close quarters like cosmic fireworks in a confined space. But it also raises new questions. How did these galaxies grow so dense? Did they form this way, or were they sculpted by collisions we can no longer see? And why, in some cases, does the oxygen appear to predate the galaxies themselves, as if the element was woven into the cosmic fabric before stars even ignited? The oxygen anomaly forces a humbling admission. For all our advanced telescopes and supercomputer simulations, the universe's first chapters remain full of surprises. Perhaps we've underestimated the creativity of cosmic evolution, that in its youth the universe experimented with recipes we've yet to imagine. Or maybe, just maybe, we're glimpsing the fingerprints of physics beyond our current understanding, where elements form through processes lost to time. One thing's certain, every time we peer deeper into the past, the cosmos reminds us that its history isn't written in stone, but in stardust scattered with mysteries we're only beginning to decode. From vanishing stars to diamond planets, from ghostly galaxies to mysterious signals that might, just might, be messages from another civilization, we've journeyed through 25 moments that left even the brightest minds in space science utterly stunned. Each one of these discoveries serves as a humbling reminder. The universe doesn't play by our rules. It thrives on the unexpected, revealing its secrets only when we're bold enough to look deeper, to question harder, and to accept that even our most cherished theories might be upended by the next observation. Think about it, scientists once believed we had the cosmos neatly figured out, only for reality to hand them an exploding black hole, a star that disappeared without a trace, or a void so vast it defies all logic. These aren't just footnotes in astronomy textbooks, they're cosmic wake-up calls proving that reality is wilder, stranger, and more inventive than anything we could dream up in fiction. And here's the thrilling part, this is just the beginning. Every discovery peels back another layer, revealing fresh mysteries begging to be solved. What else is lurking in the darkness between galaxies? What secrets hide in the whispers of neutrinos or the echoes of long-dead stars? The universe is an endless puzzle, and we've only just begun to piece it together. So stay curious, keep looking up, because the next groundbreaking revelation, the next moment that rewrites the textbooks, could happen tomorrow. And if you love unraveling these cosmic enigmas as much as we do, make sure to subscribe so you never miss a discovery. The universe has infinite surprises in store, and we're just getting started. Who knows what shocking truth awaits us next? The only way to find out is to keep exploring.